You wish to estimate the mean number of minutes that it takes to drive to work every morning, so you start to collect data every day during your commute. You collect data for 50 days straight and find the mean number of minutes it takes you to drive to work is 23.14 minutes. You also know that the population standard deviation for all the days that you've ever driven is 3.21 minutes. Build a one sample z interval to estimate the true mean number of minutes that it takes to drive to work with 90% confidence. So let's break down what we're trying to do here. This is asking us to estimate the mean number of minutes for all the times that we commute. So that would be our population parameter of interest mu, which represents the mean number of minutes for our morning commute. So from here, we're going to start by doing our one sample z interval. So let's go ahead and remember, what does this interval estimate look like? Well, we need our best guess, our point estimate, which if we're trying to estimate a mean of a population, well, we'll just take our sample mean x bar as our point estimate. And then we know that this x bar may vary depending on our sample, so we need to build our margin of error, how much we think it might be varying around the true mean, which is going to be the number of standard deviations away that we know it's going to vary. So that again comes out to our z critical value times sigma over the square root of n, which is the standard error or standard deviation of our x bar. So let's see if we can find all the pieces of information that we need in order to build this interval. We need to go through each of these numbers and plug them in as needed. So the first thing that we notice is that we're collecting data for 50 straight days. So that would be our n. That's how many pieces of data we have. And we find from that sample of 50 that it takes 23.14 minutes. So that's our x bar. Then we have the other piece of information that's given to us is the population standard deviation is the 3.21 minutes. So that's what sigma represents. So the only thing that's missing to us right now is if I want to be 90% confident, how many standard deviations away do we need to go? What is that critical value, that distance we need to go to capture 90%? So let's draw a quick picture of this. We're trying to figure out, if I know where the mean is, I want to know how much is going to vary, so that way it would be some distance 90% of the time. And these values would represent our C star, right? How far we go up and down. And so what do we use to find that? If this is following a normal distribution, we're just going to use the normal calculator. So let's jump over to our calculator that we're going to use, which is the art-of-stat calculator. So on artofstat.com, you'll see that we have these web apps here. And so that's the one we're going to choose. Or you can always just go straight to artofstat.com/webapps. And we need the normal calculator for the normal distribution. So we'll scroll down till we get to our distributions. And we'll see that the normal distribution is right here. So this is the one we're going to select. Now you remember that there's a couple of different options that we have for the normal distribution. We can either find a probability, if we know the boundaries, or we can find the percentile, which is the boundary. And this is the one we're looking for. We know the percentage, the probability. I want it to be within 90% of the time. And we need to know, what is that within boundary? How far can I go left and right? We are looking for a z-score, so we'll leave this at 0 and leave the standard deviation at 1. And again, we're trying to capture in between, so we need the two-tail. And how much are we trying to capture is the given percentage that we're looking for. So right now it's automatically set to 95. I want to change this to 90% because we want to be 90% confident. And here is where it gives us our critical values. So we can see 1.645 and negative 1.645, and we'll just take the positive version of this. So that gives us a z star of 1.645, and negative 1.645 will capture 90%. So that's what we'll use as our critical value. So this gives us everything we need. We can now perform our calculations. So plugging in the values, x bar was 23.14, plus or minus our z star, well, we're going to go 1.645 standard deviations away times the standard error, which was our standard deviation of the population, 3.21, over the square root of n. So if we work this out, we'll just do a little bit of the math here. So if I multiply 1.645 times the standard error into a calculator, this will give us 0.747. And when it's in this form, this is where we have it, where we have our point estimate as we already started with, but the 0.747 is our margin of error, or how much variation we expect to see in this point estimate. So we know that, or we hope that we're going to be within this distance of the true mean. And so this can lead now to the actual range of values, because we're just going to go up by this amount and down by that amount, and it'll give us two values. So if we do the plus version first, 23.14 plus 0.747, this is going to give us the upper value, which is 23.887. And if we do the minus version of this, so we'll change that to a minus and go down by our margin of error, this will give us our lower value, our lower bound, which is 22.393. And so we can fill in our interval. And there's our calculation for the 90% confidence interval. So what does this interval represent? Again, the whole purpose is we're trying to estimate the mean number of minutes. So what we might say about this interval is we might say something like we are 90% confident that this interval that we found, 22.393 to 23.887 minutes, what about that interval? Well, it actually contains what we're looking for, which is the mean number of minutes for our morning commute.